In this video, I will be talking about GANs. Before we understand what GANs are and how they work, we need to know what generative modeling is. It is an unsupervised learning task in machine learning that involves automatically discovering and learning the patterns in input data in a way that the model can use them to generate new examples that could have been drawn from the original dataset. In simple terms, given training data, generate new samples from the same distribution. It addresses a core problem in unsupervised learning, that is density estimation. Few types of generative models are variational autoencoders, Boltzmann machine, and GANs. So what are GANs? Generative adversarial networks, or GANs for short, are an approach to generative modeling using deep learning methods such as CNN. They are a clever way of training generative models by framing the problem as supervised learning problem with two submodels. But why do we need to care about GANs? They are achieving state-of-the-art results in a large variety of image generation tasks. They are stimulating new theoretical interest in min-max optimization problems at smooth games. GANs achieve hyper-realistic image generation by using models such as style GAN, high-resolution image synthesis using conditional GANs, and even significant amount of research has been done in the area of video generation by developing models such as SmokoGAN, TGAN, VGAN, and many more. Coming to the GAN model and its architecture, the GAN model basically has sub-neural net models known as discriminator and the generator. The generator here is used to generate new examples, and the discriminator tries to classify the examples as either real or fake. They are trained together in a zero-sum game until plausible examples are generated. Coming to the architecture of a basic GAN model, we have a latent random variable, a generator, samples generated by the generator, and a set of examples taken from the real world images which can be considered as the training dataset, and the discriminator which we use to classify these set of examples as either real or fake, and then a loss function to calculate the loss and then to improve the accuracy of the model. In order to understand how a GAN works, we can take a simple example and understand the process that takes place in the architecture of a GAN. So let us take a training dataset consisting of images of cars of different kinds of models, and we initialize a random noise vector. Let us assume it as Z, which is taken from a Gaussian distribution, and then this random noise vector is passed on to the generative network, which is trained on the dataset containing images of different cars. So what this generative network does is it by basically using the features that it has extracted from the training dataset, it maps through the latent space and then it generates fake images. Now these fake images and the real images are passed on to the discriminator network here, where the task of the discriminator network is to distinguish between these images as real or fake. After distinguishing them as real or fake, the cost is calculated, that is to figure out the error rate between the predicted outputs that you would expect to see and then what actually has been generated by using cost functions such as binary cross entropy, and then the backpropagation algorithm is used in an iterative manner where the discriminator and the generator network are concurrently trained together in a zero-sum game, and in the end plausible examples are generated. Although the way GANs work might seem simple and straightforward, there are a few problems when you look at them closely. The first problem is vanishing gradients. The discriminator becomes too good and the generator gradient vanishes. So what exactly happens is the discriminator is so good that no matter what kind of images the generator generates, the discriminator always labels them as fake. So no matter what the generator does, it can't um, make the discriminator believe that the images that it has generated are real. Coming to non-convergence, the generator and discriminator oscillate without reaching an equilibrium. Mode collapse. The generator distribution collapses to a small set of examples. In mode dropping, the generator distribution doesn't fully cover the data distribution. These are a few problems that we face while working on various GAN models. However, there are a few solutions that have been proposed and implemented. One being which is called as label smoothing, and also with the use of optimizers such as the SGD, that is stochastic gradient descent, and the Adam optimizer. The training of the model can be made stable, and it can help in increasing the accuracy of the model. The other approach is to basically use hybrid models where you can use a variational autoencoder along with a GAN to stabilize the whole training method and to make the process of generating images less tricky. Another method is basically the use of um, Wasserstein GAN. It was a theory that was proposed and later implemented, which resulted in really good accuracy scores, where the Wasserstein GAN basically stabilized the whole uh, GAN model, and it was able to generate proper images, and which also helped in um, making sure the discriminators capacity to learn and to ensure the vanishing gradient problem doesn't exist is completely removed. There are a few applications for the GAN models, one such being image super resolution, where it is the ability to generate high resolution versions of input images, creating art, the ability to create new and artistic images, sketches, paintings, and more, image-to-image translation, the ability to translate photographs across domains such as day to night, summer to winter, and more. Um, Here are few images that have been generated using the cycle GAN. Here, the image of a horse, when given as an input, it was converted to a zebra, the same being from zebra to horse. A similar kind of translation has been done here, where a crate of apple has been converted into a crate of oranges, and the same thing being from oranges to apples. Here, the season has been changed, that is from winter to summer and then summer to winter. In these particular images, the background has been blurred so as to increase the focus on these flowers. In this set of images of different kinds of bedrooms, these have been completely generated by using GAN models such as the LS GAN. And coming to these images of people, these are basically images of uh, uh, humans that do not exist in the real world. These are completely fake images. So one good application of using GANs is to generate synthetic data, which can either be images or videos, which can help in reducing the cost of human resources and time that are generally um, used to manually create data sets in order to train much more larger modules, which are used in applications such as object detection and many more. So concluding the topic of GANs, we can understand that they take a game theoretic approach, that is learn to generate from training distribution through two-player game. The pros are beautiful state-of-the-art samples are generated. Cons: the way GANs work might be trickier to understand, and it is also more unstable to train. Active areas of research include trying to develop better loss functions, more stable training, such as the Wasserstein GAN, LS GAN, and few more, and then the use of conditional GANs for various kinds of applications. Thank you.